Okay. Good afternoon, everyone. Welcome to today's webinar, Detonation Instabilities in High-Speed Flows, part of the ASPCC pre-conference webinar series. I'm Xiaodong from National University of Defense Technology in China. My research is all about supersonic detonation combustion. And I'm really happy to be your moderator for this session. Detonation instabilities are a big hurdle in developing high-speed propulsion systems, from detonation engines to the latest aerospace tech. Today, we are lucky to have two top experts who are doing groundbreaking work in this field. Our first speaker is Dr. Zhaoxin, a senior lecturer at Swans University's Xian Institute for Modeling Data and AI. Dr. Ren is a specialist in computational fluid dynamics with a focus on high fidelity simulations of multiphase and reactive flows. His work on propulsion systems and hydrogen life cycle assessments has led to collaborations with top aerospace organizations, and he's also an associate editor for the Journal of Renewable and Sustainable Energy. Today, he will talk about three-dimensional detonation dynamics, looking at how thermal confinements shape detonation wave structures in rotating combustors. Let's welcome Dr. Zhaoxin Ren. Okay.
Okay, hopefully you can see my screen now. Thank you,
Yes.
Professor Tsai, for the invitation. So I'm Zhaoxin, and from the Zinkvich Institute for Modeling Data and AI at Swansea University. And today I will be discussing my research on the three-dimensional rotating detonation structures with a focus on the influence of the thermal boundaries. Okay, so the first is the motivation. So the motivation of the research, so we wish to improve the efficiency of the conventional engines. Okay, this has become increasingly challenging. So an alternative approach is to explore different methods to converting the thermal, the chemical energy into the thermal energy. So one such, the changing method is the combustion with pressure gain, which is also, we call it detonation. And the target of the detonation-based engine, okay, is to enhance the performance and efficiency by changing the thermodynamic cycle. Okay, unlike the conventional combustion, the detonation is an unsteady process, which the gas expanded from heat released and in the confined space, which lead to a rise in the stagnation pressure, and this can help to extract the work through the expansion into the initial pressure. We can see that there will be some different propulsion applications based on this detonation. For example, because we can see the traditional engines, for example, the gas turbines, it primarily use the diffusion combustion. And for some rocket engines, it use some like premix combustion. So on the contrary, so the detonation engines offer uniforming solutions. The same system can be adapted for gas turbine, ramjet, and rocket engine. From the practical standpoint, the conventional combustion chambers are typically cylindrical, okay? But the detonation engines do not need some typical geometries because you can see that detonation is a surface level chemical reaction. So this means we can build the system, the combustion chamber, more flexible or for some different configurations. For example, you can see that the top left, which shows the conventional configuration, with two cylindrical cylinders and the flow channel where detonation occur. And if this setup compressed, you can transform into a racetrack shaped detonation system. You can see the top right figure. For the bottom left, illustrate some for how the detonation can be integrated into the ramjet or scramjet. So this highlights that we can build different configurations or different shapes of the structures of the for the detonation application. If we see a typical rotating detonation engines, we focus on the flow inside. And this is two concentric cylinders with the detonation wave propagates into the inside in the circumferential directions, and fuel and air are injected from the bottom. You can see the left side figure. And the combustion occurs at the detonation wave consumes the mixture. So because it's a highly compressed system, which involves some compressor flow interactions and the mixing dynamics and the wave phenomena. And you can see that detonation wave, the front itself is very thin. It's usually the order of sub-millimeters. So that means that compared with the size of the detonation wave, the chamber can be maybe meters in size. So that means the scales, the length scales will cross a very wide range from millimeters to meters in the whole engine size. Another one, to reaching a steady state can take several seconds. But the detonation wave is very fast. That means this whole flow scenarios will across a wide range of both length and time scales. So this complexity makes the detonation flow simulation is, in terms of the computation cost, is very challenging and is one of the most difficult flow problem to study. So if you check the detailed structures of the detonation waves, you can see that they are not smooth surfaces. Okay, instead they exhibit some cellular formations with some concave and convex features. These structures play a crucial role in sustaining the detonation propagation. If we considering the practical application, the challenge is the thermal management, because you can see the very high pressure temperature of the detonation products. Okay, so the cooling the channel typically placed around the outer cylinder. However, the influence of the cooling boundaries on the detonation structures remains unknown to us. Okay, so which this the cooling the boundaries, the influence of cooling on the detonation structures motivate our research. So for the simplicity, we do not consider the curvature of the cylindrical channel. Instead, we model a three-dimensional linear periodic channel. You can see we unwrapped the 3D annular combustion chamber to the straight linear channel, like a replacement, to see the propagation of the detonation wave in this linear channel. You can see that the primary structures in this linear channel is closely similar to the flow structures in the annular chamber. By modifying the thermal conditions on the wall boundaries on each side of the channel, we try to analyze the influence on the detonation propagation and structures. So in this presentation, I will cover first our computation approach, and then we analyze the three-dimensional structures under the adiabatic confinements, boundaries, and then we try to study some effects of the thermal confinements. For example, we change the wall temperatures after the cooling to see how the behavior will change. So we use some high order schemes to capture the dynamics of the detonation waves, and we use the kinetic gas theory to model the transportation properties. And before the simulation, we did some more validations. For example, we compare the cell size, we compare the detonation speed, compare with the experiment database. We choose some proper inlet conditions to mimic a ramjet mode of the detonation engines flight at 25 kilometers height, and the flight Mach number is about 4.55. And we choose 3 cases to mimic different scenarios for the thermal confinements. For example, for the inner wall and outer wall, we choose adiabatic and also the isothermal conditions to mimic the wall after the cooling. So this case, IAOA means the inner wall and outer wall are both adiabatic. And for the ITOT means the inner wall and outer wall, both of them are isothermal with 300 Kelvin after the cooling. And for the case IAOA, which means a mixture confinements, which is the inner wall is adiabatic and outer wall is the isothermal after the cooling. So first we have a look at some structures and under the adiabatic walls. Okay. So the adiabatic walls means there's no heat transfer across at walls. We can see that there's a single detonation wave propagates through the channel, as shown by the right side, the sectional views of the pressure fields and also the temperature fields. Okay, if we choose some 2D planes across detonation front, we can see that some regular cellular structures with uniform cell size. Okay, so we can see the structures is uniform if we see the pressure distribution. And if we choose the isosurface of the static pressure, which we can see on the left side of this figure, it highlights the detonation kernels. You can see it from the red pocket, which forms as the transverse waves collapse. We can term these detonation kernels as multi-kernels. Okay, so they are from more than 2 transverse waves intersecting, and the multi-kernels can generally have more extreme states. You can see the higher static pressure from the detonation kernels. And the evolution of the cellular structures is shown by a series of 2D slices on the right side, revealing the quasi-square lattice patterns as regular structures. Then we apply some cooling on the boundaries, okay, which means the wall is after cooling, we can see some different scenarios. Okay, so again, we can see from the XY 2D plane, it shows like a double wave structures with a stronger detonation front followed by a weaker wave. Also from the temperature fields, we can see the unburned reactive mixtures will occur in the domain, in the chamber. If we make a 2D plane across the first detonation front, it shows like some striped-like cellular structures. okay, which has a clear directional preference, which is different from the case with the adiabatic boundaries. So from the isosurface of the stacked pressure on the right bottom figure, you can see the majority of the white bandings which appear transverse along the direction which is perpendicular to the propagation of the detonation wave. Then these transverse waves will collide with the walls and the detonation kernels, which shown by the red spots, can be termed as the line kernels, which are different from the multi-kernels. The line kernels, which is resulted from the two transverse waves intersecting. From the temperature field, we observe some vortices generated within the boundary layers, which has a large temperature gradients. If you see the second weaker wave following the first stronger detonation wave, this is due to the wall interaction of the wave impacting on the wall and reflect back. Okay, then let's examine the evolution of the wave structures. We can see from the animation, first is the detonation wave, and then the wave propagates on both sides and then collide with the walls. Then a pair of the waves reflect and interact to form a stronger wave, which is the second detonation wave. So that means when the cooling is applied on the walls or boundaries, so we can see that detonation structures is very different from the typical structures we can examine, we can see under the adiabatic conditions. Okay, so we have another test on the mixed thermal confinements, which means one wall is adiabatic and another wall is cooled after cooling. So you can see why we make this mixed thermal confinement, because you can see that in the practical application, usually maybe it's easier to cooling the wall at the outer wall of the combustion chamber. So we have some test on this mixed thermal confinements. First, we still check the pressure fields. Okay, from the pressure fields, we can see the single detonation front. But if you check the temperature distribution, okay, it has a different flavor. So we can see the second flame following the first detonation front. And also, there are some unburned reactive pockets in the combustion chamber. Again, similar to the previous analysis method, we make a cross-section along the detonation front. On the right figure, you can see that it's also the cross sectional plane, 2D plane. You can see on the outer wall is really is 300 Kelvin is after cooling, and inner wall is adiabatic. So we can see that the detonation structure seems like a combination of those structures we previously seen from the cooling and the adiabatic boundaries. We can see the lower part is similar to the structures under the adiabatic confinements, where we can see the upper part is similar to the structures under the cooling conditions, resulting the whole scenario is like irregular cellular structures. If you see the temperature distribution, we can see similar things, because we can see the outer wall is because it's cooling, so we can see thermal boundaries will occur near the wall. So here's the dynamic process, we can see there's a very strong wave-wall interactions, which result into this irregular detonation structures. You can see the wave propagates towards the cooler side and reflects from the wall and returns back. Okay, here we have some comparison of the three cases we apply in the study. It can be concluded that the thermal boundaries do have an impact on the detonation structures. Not only the number of the detonation waves, but also we can see the three-dimensional detonation structures. Then I would like to have a look at the dynamics of the cellular structures, which is analysis based on the maximum pressure history. So this figure shows the 2D slice from the channel. And if you see the adiabatic boundaries, which produce a detonation cells, which appear more regular. Okay, you can see the maximum pressure history. And here we can see for the adiabatic boundaries, these have similar size for each cell. If you see the case with cooled walls, cold channel, on the other hand, has no clearly regular detonation structures, okay, as shown by the random white bandings. In particular, the cells are longer in the directions which perpendicular to the propagation direction of the detonation wave. And the elongation patterns of structures is more obvious, you can see near the wall boundaries. And for the mixed thermal confinements, and the cells near the cold wall are stretched. You can see here, here. And the size of the cellular structures are near the hot boundaries are more regular. Okay. If you see the maximum pressure history on the walls for the case with mixed thermal confinements, if I would like to see this maximum pressure history on the wall, which has the cold temperature, we can see many white straps here. Okay, this is the traces left by the wave and wall interactions. Okay, at last, we want to see some the pressure signals which collected by as the fixed observation point. And these profiles provide some insight into the peak pressures of detonation waves. And it's interesting to find that the case with cooled walls, okay, can show a highest pressure, detonation pressure, but we can see that also demonstrated very significantly in instability with some large fluctuations of the detonation pressure. And based on the pressure signals, we calculate the detonation wave propagation speed. And initially, the case without cooling have the fastest speed, but after some unstable phase, the cases with the cooled walls show some similar propagation speed to the adiabatic case. Okay, so we go to the summary of the research. So we can see that the thermal boundaries can significantly influence the detonation structures. We have some regular structures under the adiabatic thermal confinements, but we see some irregular structure patterns under the cold boundaries, with some strap-like structures. And we can find two types of the detonation kernels, which is multi-kernels under the, which is regular kernel under the adiabatic thermal confinements, but we can see some linear line detonation kernels under the cold thermal boundaries. And the mixed confinements, which shows hybrid structures with asymmetric wave behavior. And if you see the pressure signals, we can see the maximum pressure signals reveal that the cold cases exhibit shows the highest peak pressures, but also the most instability. Some features show that we should, if we're considering the cooling, okay, we should carefully design how much we can handle the temperature and at the wall boundaries. For the future work, we would like to detail some parametric studies and do some experiment validation to further refine our understanding. So why the irregular detonation structures will be occurred under the cooled thermal confinements. Okay, so that's my presentation, and thank you for listening, and welcome any questions or comments.
Okay, thank you, Dr. Ren, for that really interesting talk on how thermal confinement affects detonation dynamics. Your insights into computational modeling will definitely help us optimize propulsion systems. Now, let's open the floor for some quick questions. Any questions? Okay, I have one question. In this topic, Dr. used two different thermal confinement conditions, right? One is adiabatic and the other is cooling, 300K, right?
Yeah. It's isothermal conditions with just a constant 300 Kelvin as we assume there's a cooling.
Yes, I think yes. I think in practical applications, for example, if you use the adiabatic confinement, I think maybe the wall temperature will be very high.
Yeah.
That the structure of the engines might not be able to maintain its shape or its strength. And this is one question. And the other, if you use the cooling condition, for example, 300K, right? Maybe you use too much heat sink to decrease the temperature to 300K. Maybe I think the more close to the real applications is that you can use for example, 8K, 800K or 900K. This might be more close to real applications, thermal confinement, right?
Yeah. Thank you, Professor Tsai. Yes, it's true that if we use 300K, it's like a big drop from like combustion products which has the 3000 Kelvin to 300K. It's a big drop and a very huge heat sink. Yes, it's like some moderate temperature, for example, 1000 Kelvin or 800 Kelvin will be more close to the practical application after the cooling.
Yes.
Yeah. That can be considered for the next step study. Yeah. Thank you for the comments.
Yes. Okay. This is the first presentation. Thank you all for joining in. Let's give another round of applause to Dr. Ren for his insightful presentation.
Thank you.
Next up, we will have Professor Ralf Deiterding from the University of Southampton. Professor Deiterding is a well-known expert in numerical methods for fluid dynamics. He has over 180 publications and has led to the development of an open source simulation frameworks like ARMROC and the virtual test facility. His work at places like Caltech and Oak Ridge National Laboratory has really pushed forward high-resolution simulations of detonation phenomena. He'll share high-resolution simulation breakthroughs showing us computational methods to capture instabilities in complex geometries. A warm welcome to Professor Ralf Deiterding.
Hey, thank you very much for the introduction. Quickly, that I share this correctly here. Okay, I think I'm sharing correctly now. It's a little bit difficult. So thanks again for the introduction. So in this presentation, I'll be showing results from my former students, particularly Han Peng and Chai Atkins. And then I have also some results from recent work with Alexander Marshak. So as mentioned during the introduction, our objective is particularly also on constructing numerical methods. So I'll go a little bit into the detail of the computational methodology that we use in order to simulate detonation waves and where we have spent the time recently. Then I have some verification and validation results, some common test cases that people use in the detonation field. And then in the second part of the talk, I talk particularly about detonation propulsion, and there I equally have results about rotating detonation engines and equally with different temperature boundary conditions. So as mentioned in the introduction, I have put on the internet the MROC framework, and MROC is a system to do structured mesh adaptation on Cartesian grids. First of all, it works such that rectangular grids are overlaying one another, and then these grids talk with interpolation and restriction operation with one another. And mesh adaptivity is particularly important for detonation waves because the interaction between the fluid dynamics and the chemical reaction is nonlinear, and you need quite some high resolution to capture that correctly. And MROC originally in that form, Cartesian, of course, is not particularly suitable, for instance, to rotating detonation engines. And the original version of MROC is Cartesian and uses embedded boundary techniques to consider complex geometry. But for instance, if you're solving Navier-Stokes equation with a boundary layer using Cartesian grids can be quite inaccurate. And of course, a rotating detonation engine is best modeled with a cylindrical mesh. And this is why we recently have put a lot of effort into moving to curvilinear meshes. So the first work that we did into this direction was with my PhD student, Chai Atkins. And that wasn't for classical combustion. That was for hypersonics, meaning we have particularly thermodynamic non-equilibrium with multi-temperature models and also chemical non-equilibrium from air dissociation. And the kind of software that we constructed here in 2D is an overset mesh technology where we have Cartesian adapting background meshes. And then near the surface of a body, we use body-aligned meshes that are grown in the normal direction to the surface. And then these meshes talk with one another through overset interpolation operations. So you see here at the red cells, this is where interpolation communications have to happen. And we then use this particularly to study typical hypersonic applications. Like for instance, here is a double wedge in axial geometry. So it's actually symmetric. And then, of course, a shock wave is forming. And when we zoom in a little bit, yeah, you see that, of course, the shock waves, etc., are dynamically captured by the Cartesian mesh. And then the boundary layer near the embedded object is captured with its own non-Cartesian mesh. And in hypersonics, it's all about the temperature in the boundary layer. And so then this boundary layer here is resolved very well. And this model uses two different temperatures, one for translation and rotation and another one for vibrational temperature, as it is depicted here. And so then the chemical reaction, in this case, this is evaluated with a mutation ++ library. So based on this work, then in a sequence of papers, Han Peng has been able to extend this methodology, particularly to combustion problems. So here we then solve fully in 3D, and you will see results about that, the Navier-Stokes equation, in the form that are typically used for combustion modeling. Like in hypersonics, the heats of capacity are temperature dependent, but here we take then the values from the Janov table in the form of fourth order polynomials. We use the Chemkin library to evaluate the chemical reaction. Mixture viscosity, mixture conductivity, diffusivities, they are all evaluated with Chemkin standard routines. And while in hypersonics, we usually model the degrees of freedom in the gas directly. Here, because the data is in a polynomial form, we usually go through a form of the energy equation that we effectively have to solve inversely to obtain the temperature. Here, of course, in combustion, only one temperature. It's thermodynamic equilibrium, so vibration is not specially considered. And then we use typical Arrhenius kinetics with only one temperature through Chemkin to evaluate the reactive terms. Here, the method that we are using, of course, we are using a splitting method. So we solve then the chemical reaction terms in each finite volume cell. And we do this still today with a fourth order semi-implicit Rosenbrock-Wanner method. And we use the same method also for the hypersonic, where we have the non-equilibrium source term in addition, and that method works exceptionally well. Of course, when we want to go to non-Cartesian measures, we have to extend the finite volume formula. We have to consider the change in volume due to the mapping and, of course, the different area of the facets. Here we use a form that is called capacity differencing. In this form, we solve the convective fluxes and then the viscous fluxes. We add them together. And then when solving for the convective fluxes, we do this with a Riemann solver. And the Riemann solver, of course, we had from the Cartesian framework. So what we then do is we have a transformation matrix T that implements a rotation from the physical coordinates to the computational coordinates. And then we apply the prior Cartesian Riemann solver, and then after having obtained this flux in Cartesian form, we rotate it backwards with the inverse of the transformation matrix. The convective fluxes, in our case, they are then enhanced to second order with a Mussel-Hancock approach. And then the viscous fluxes, they are added as central differences in finite volume form. And because here in this formula, we are adding both fluxes together, we then in the CFL condition, we have to add this to the convective CFL condition. So for the convective fluxes, we use Riemann solvers. So, and we first of all, we used the row scheme that actually dates back to my own PhD thesis. We combine this with an HHL scheme, and it is combined such that within the Riemann problems, we evaluate the intermediate states if there is a problem with the state vectors. So the row method can undershoot in pressure and in energy, particularly in a vacuum situation. And when that occurs, we switch to the robust and positivity preserving HHL scheme. And that is important for the robustness in particular applications. And of course, the row method also has entropy correction and carbuncle correction. A problem that we encountered, particularly with the row scheme, when doing non-premixed computations of rotating detonation engines, that the very classically known problem is that when the heats of capacity vary considerably in different species and they are non-premixed, that pressure perturbations can occur purely of numerical nature. It's a very classical problem in combustion. And here it was rather pronounced with a row scheme. And so here we then often switched to the HHLC scheme. So this is the HHL method with a restored contact discontinuity. We take here very much the standard scheme. And while this method does not entirely eliminate this pressure problem, it mitigates it to an extent that it is practically usable. Here is no carbuncle correction, but it is also not a problem in the cases that we considered. So in order then to construct an adaptive mesh method on the curvilinear mapping, you of course also need to extend your AMR machinery. And while you can use the communication between grid patches, etc., that is all happening in an index coordinate system, you have to extend the transformation operations that do the averaging and the linear interpolation. Of course, you need to consider the volumes when averaging, and you need to consider the change in central location of the finite volumes when interpolating. And the final operation that is often overlooked is in these structured mesh methods. One first updates coarser grids, and then one moves over to the finer grids using coarse grid data as internal boundary conditions. When then projecting the data backwards down at the end of the time step, this typically leads to an error in conservation because the fine grid fluxes have not been properly considered for the force grid interfaces. And so this is then implemented as a fix-up step. And here we also then implemented this fixed-up step on the curvilinear grid, considering the facet size. And then when we do this, we have no conservation error until machine accuracy. So the first test cases, and these are very classical test cases for detonation solvers that I want to consider, is the projectile experiment by Lea. So what we have here is we have hydrogen, oxygen perfectly mixed, and then small projectiles of 1.5 centimeter diameter are shot into this mixture. And the trick is they fly at a velocity close to Chapman-Joget detonation velocity. And then you get detonation features in the front of the projectile, particularly in the stagnation point. In the stagnation point, so we have seen in the prior talk, the formation of transverse waves along detonation waves. And then this feature happens exactly at the stagnation point. And for different flight velocities, you obtain different perturbation frequencies, very characteristic in nature. So, and that's one of the most important benchmarks for detonation computations, and results on prior computations by different people have been quite diverse. So here, this problem is simulated with a strictly Cartesian method, and we see here the front of the projectile, and here we then see the entire projectile, yeah? And you see when this is running, this is now with a Cartesian grid solver, you see the formation of transverse waves and how they are forming very regular structure then over the projectile. And here we see the dynamically adapting Cartesian meshes following this behavior. And so this is at a resolution of 9.4 micrometer. And this is using the Yachimovsky mechanism. And so when we ultimately then used here the Navier-Stokes equations for this problem, we got within 8 kilohertz into the experimental measured frequency for this velocity 4.48 Mach. And when for the Euler equation, you see that the error is accordingly larger. So that was a while ago. And then we moved on to that, to the non-Cartesian meshes that gave us the opportunity, particularly to focus the mesh even better in the central region where the perturbation originates. And here we very easily then, with also using the adaptive mesh, we were able to use then very easily resolutions of 3.5 micrometer. So here you see two different cases at 4.18 Mach number. So perturbation here is slower. And then at 4.48, this is a case from the prior slide, the oscillation frequency is higher. And then here, with this new method, and then using the Yachimovsky mechanism, we effectively hit for the Navier-Stokes equation, we hit the experimental frequency perfectly. What we notice is then if we go to the lower Mach number, suddenly we have an error in the perturbation frequency again. We then switched to another hydrogen-oxygen mechanism, the UCSD mechanism, and then we hit that one. But using then the UCSD mechanism, if we want to do the 4.48 Mach number, suddenly we are back at an accuracy of the prior method with the Euler equations. So yeah, here you see this with even higher levels of resolution. And what we see on this kind of grid study is that already here at a resolution level of 7 micrometer, we are hitting the perturbation very well. Yeah, here we see the different refinement criteria. So what one can summarize from this test cases is that fluid mechanically on the CFD side, we are in well shape to solve these cases with very, very good accuracy. But the problem that arises here for this very popular test case is that at least to our knowledge, there is no hydrogen-oxygen mechanism that would be able to simulate all the different measured frequencies at different detonation velocities that are experimentally available that would hit this computationally. And that has turned out to be the weakest link, the lack of a reaction mechanism over all the ranges of available experimental results. And that is a reason, of course, why people have reported somewhat ambiguous results for this test case. Yeah, the variation, particularly in reaction mechanisms. So then we moved on to three-dimensional simulations. And here, this is a verification validation simulation where we propagate a very regular oscillating detonation structure that we had computed before. So we projected as initial condition into the mesh, and then the detonation propagates around the pipe band. Yes, so you see this here, how the detonation is propagating around the pipe band. The dynamically adaptive mesh follows perfectly, and the adaptivity is very effective here, so we easily save a factor of 50 in computational effort. The structures, due to the regular boundary conditions, are equally very regular, and then the detonation goes particularly through the band, and we see a typical decoupling between the shock wave and the flame front of the detonation. And you see here that the experimental results from this macroscopic perspective and the detonation agree very nicely. Another case that we did, a typical instability in detonation waves, is when a detonation wave encounters a boundary layer. So here we use the adapted mesh within the domain, and then particularly the map mesh capability to resolve the boundary layer perfectly. So in that case, when interacting with a boundary layer, detonations undergo shock boundary layer interaction, and then the shock wave particularly shoots forward. So we see this here in this animation. The detonation goes rapidly unstable and shoots forward, and then an original planar detonation front becomes entirely perturbed. Yeah, so that is a typical feature of such computations. So if you don't want to deal with detonation and shock boundary layer interaction, what do you have to do? Well, you have to bleed away the boundary layer. So here we do a very realistic real-world computation of an oblique detonation combustor. That's an experiment by Zhang. And you see there is, after the inlet ramp, there is a bleed device that eliminates the boundary layer. And this case, it uses hydrogen injection, and it is very three-dimensional in reality. So the inflow conditions are not well known. So for us, this was an inverse problem where we had to determine inversely from experimental results the actual inflow conditions, particularly the stoichiometry that is present in the combustor. That's the reason why we then, with our Cartesian method, we simulated the entire scenario. Yeah, and then here we get here in the combustor, we get this oblique detonation phenomenon. So then zooming in on that, so you see here the experimental Schlieren image, and here our computational image. Here the mesh adaptivity that automatically has been generated. So the agreement is not 100%, and the reason for that is that we effectively, particularly the stoichiometry within the mixture at the combustor, we are solving this inversely, yeah, by doing many computations. Determine that, but you can see we do a reasonably good job because the agreement of the experimental results versus our computational results of the pressure at upper and lower boundary is actually quite decent. So yeah, with this methodology, we then particularly move on into rotating detonation engine simulations. We have seen the features of a rotating detonation engine wave already in the prior talk. And so here are computations in 2D. So when you use premixed injection conditions, that is very common in 2D. Of course, then the mixing is perfect, and we get a very perfect detonation phenomena. So the detonations that propagate within this combustor then usually propagate exactly at the ideal detonation velocity, at the CJ speed, at the Chapman-Jogues speed. If we use non-premixed conditions, the situation is heavily perturbed. And of course, mixing is one of the primary loss mechanisms in rotating detonation engines. And then here, effectively, for the same configurations, we only get one detonation wave. I think the mixing in 2D, that is actually the most problematic because there is no such thing as 2D turbulent mixing. So you really have to do 3D to get the mixing even reasonably right. So the configuration here that we are doing is now one of hydrogen air in a rotating detonation wave. It's a configuration from the Air Force Laboratory in the US, and we simulate this case, and you see that the injection here is perpendicular to one another in the injector. So here are different resolutions of this configuration. They all kind of converge reasonably well to the same behavior. And what is interesting is how well do these computations actually agree with experimental results. So that is then evaluated here in this investigation, where we particularly increase the mass flow rate. And so generally, as larger the mass flow rate, as fewer the loss mechanisms in rotating detonation engines. So you see that experimentally obtained detonation speed as well as simulation speed agree better and better. When the engine is smaller, when the mass flow rate is smaller, the discrepancy is larger. Also, particularly discrepancy is that the number of heads that seems to be predicted, so how many detonation waves are present in the combustor, is slightly different. However, that is a somewhat ill-conditioned problem because it's a bifurcation problem, how many detonation heads you are getting. And what is a better measure is if we sum up the length of all the detonation heads, because this is where detonation combustion then really happens. And from a macroscopic perspective, this is all what matters. Then if we compare that, the agreement is quite well. So if we compare here static pressure within the engine with experimental results, yeah, so our results are the triangles. So we hit the experimental result actually quite well. So we then used this configuration with an inflow of 320 grams per second to vary actually the temperature boundary conditions. This is very similar like in the prior talk, where we use adiabatic wall boundary conditions. Yeah, so here we see 3 detonation waves that are propagating, and then we varied the wall temperature and prescribed it at 300, 600, and 900 degree Kelvin. Of course, a 900 degree Kelvin, that would be somewhat similar what really happens in an RDE combustor. And of course, at the outer and inner wall, there is an apparent difference. Yeah, we see that, for instance, here, this at the inner wall, we get sub-combustion effects, so commensal and parasitic combustion that wouldn't be present in that form in the adiabatic case. And I think we have seen some evidence of that also in the prior presentation. However, what is particularly interesting, what is the heat flux here? Of course, when we are cooling the walls more, the temperature difference is larger, so then the heat flux increases. That is at the inner wall. So if we look at the outer wall, the heat flux, interestingly enough, is significantly decreased. In our case, we had injected the air from the outer wall, so this is one cooling mechanism. And of course, we also want to keep in mind, in a cylindrical chamber, the area on the outer side is approximately 20% larger. That's another reason why the heat can distribute a little bit better. So, but what is most interesting from my point of view is what is actually the scenario when we look at the center of the chamber. Yeah, so and when we look at the center of the chamber, you see that the number of detonation waves in time is almost unperturbed. They are propagating 3 waves, almost unperturbed, independent of the temperature cooling. Yeah, and I think this is the bottom line. Here, particularly for practical application, the cooling of RDEs is very important to make them work. And what we have found here is that different wall temperatures are not a significant loss mechanisms in RDEs, that you can cool them happily and the combustion virtually is unaffected in the interior. And that is, of course, exceptionally good news for constructing real-world rotating detonation engines. Yeah, real-world detonation engines, here is ours, a very small one in our laboratory. So this is how it is looking, and it is a very small one. It only uses less than 10 grams mass flow total. Yeah, it produces approximately 3 detonation waves, and here the loss is quite significant. So the detonation speed is only approximately 60% of the Chapman-Jouguet detonation speed. So there are a variety of loss mechanisms at present here. We are not entirely there yet to simulate that, but we are working into that direction. So here's a preliminary computation where we are injecting not ethylene and oxygen like in the real world configuration, but with nitrogen for stabilization. So here we conducted a very elaborate convergence study. So you see the typical CPU times and the number of cores where that was run. So we are predicting then when resolution is sufficient 2 heads. So that works very well. And the resolution here is very sizable because what we were able then to demonstrate is, so like in the computations we have seen in the prior talk, we can also here, we can track the evolution of the transverse waves that are intrinsically there in any detonation propagation. And then for half a detonation period until one wave hasn't reached into the prior region of the prior detonation head, we can track these structures by tracking the maximal pressure or the heat release rate, and then we can make the cellular structure visible. And so you can see here, our computation is sufficiently resolved to show that, and we find then cellular structures in the axial direction of 1.5 millimeter size. The resolution is not ideal, which you see that the triple point lines are rather straight. They should be slightly more curved when the resolution would be entirely sufficient, but the structure is definitely present, and that is quite an accomplishment for a cylindrical RDE combustor. So that brings me to the conclusion and the outlook then eventually. So I have shown you how we have constructed a 3D fully viscous adaptive solver for combustion. That is quite an accomplishment. It is based on using Riemann solvers, and savings in the right cases due to the adaptivity are easily by a factor of 50. I've shown the very frequently used benchmark by Lear, and here I think we can definitely conclude one would need a better hydrogen-oxygen mechanism to be able to simulate all the frequencies with very high accuracy. And then we have talked particularly about rotating detonation simulations. So I've shown you some premixed and non-premixed cases. The greatest challenge is in when trying to simulate real-world RDE combustors is to include all the loss mechanisms that are present. And the primary loss mechanism, in my opinion, is a mixing and the loss that happens due to realistic injector geometry. So we are still using cylindrical mesh and can't represent ideally the injector geometry. And so in the future, I think we will be putting effort to model the injector geometry more accurately. And I think this will be done then by using the embedded boundary capability on Cartesian meshes as before, and then coupling this with overset grid interpolation routines to the cylindrical combustor. Yeah, finally, because somebody might ask me about that, do you want to release a new version of that software? So as you have seen, we have quite a few applications for the new map mesh solvers, but we are still in the process of consolidating that. And what is planned for the somewhat nearer future is to release at least the mesh capability for Euler and Navier-Stokes equation for constant gamma. Not necessarily, of course, for the hypersonic case and the combustion case, but for the constant gamma case that has greater application. So that is all what I have for today, and I'm happy to take any questions.
Okay, thank you, Professor Deiterding, for showing us how advanced simulations can help us understand the detonation instabilities. Your methods are truly game-changing for both academia and industry. Now, we can have one or two trivial questions. Any questions? Any questions?
There's some question in the chat, not in the Q&A.
Okay, I can see that. Oh, there's one question for Dr. Ren, right? How does the unwrapping the channel will be done? I use ANSYS Flint for Dr. Ren, right?
Yeah, I think the straight channel, you just build the channel and use the periodic boundaries at each side, and then let the detonation wave to rotate and rotate periodically.
Okay. Any questions for Professor Deiterding? Okay, I have one question for Professor Deiterding. In the experiment, are you sure that the rotating detonation is initiated successfully?
That it is initiated successfully?
Yes.
Yes.
You can see that the velocity is about less than 60% of the CG velocity, right?
It's in this state, it is what generally is called a quasi-detonation. It is a very, very fast. So when it is this situation that you are considerably below CJ speed, you are somewhere in a situation between a very, very fast deflagration and a detonation, and people typically call this a quasi-detonation. So this phenomenon that you are at very low speeds, like 60–70% of theoretically possible CJ speed, is very common to many RDE experiments. It's very rare that people actually reach even into the 90% of CJ speed at present. So it is one of the great issues that is also, I think, in order to obtain and achieve truly pressure gain in these kind of propulsion devices, that is one of the greatest questions in this field at the moment.
Okay.
But if you are able to achieve at least around, let's say, I think 90% of detonation speed, then pressure gain can be demonstrated and measured in experiments with the right nozzles after the combustors. But with 60% detonation speed, we surely have no sufficient pressure gain, and we wouldn't produce sufficient thrust. But it is a phenomenon of very small experiments.
Yeah. Is that the reason from the total pressure loss from the injection?
I think it's a combined effect. It's a combined effect. It's as I said, I mean, the pressure losses. So there is pressure loss when the wave passes over the injectors. There is mixing loss. In a small combustor, there is also friction that likely cannot be ignored. I think we have demonstrated comprehensively with our computations that usually the thermal loss is negligible. That is good news. But how to mitigate the other ones? Particularly, I think mixing is automatically mitigated when you have a very large engine with a very large mass flow. Yeah, then mixing is rather good, I think. But otherwise, how to mitigate all the losses well and truly achieve pressure gain, these are the true research questions of this field.
Yeah.
Okay. So maybe in your next experiment, you can get the pressure history, right?
We have that.
Yeah.
We have that.
Oh,
We have that. So we have in this small experiment, we have one pressure transducer that measures the detonation wave, and from Fourier transforming the signal, this is how we know the detonation speed. This is how we measured it. What you also can do is, so I showed the picture. You can, with a high-speed camera and knowing its shutter frequency, you can backwards analyze the imagery and from that equally deduce detonation velocity. This has become more practical, and as this is more common in experimental analysis, not to use transducers, but actually to analyze video imagery.
I see. I can see another question from Carl Tatley. He says, thank you for sharing your recent works. In your cylindrical RDE simulation, you saw cellular structures, but most RDE experimentalists mention they are not present. Can you tell me again how you explain their presences in your simulation? So I think this question is for Professor Deiterding.
So the cellular structures?
Yes, cellular structures, yes.
No, the question is, are cellular structures present in RDE experiments? And of course they are present. Here, the cellular structures that we really could enlighten were in the axial direction, where the detonation is also somewhat unconfined. But cellular structures are definitely present in RDE experiments, as we have also seen in the prior talk. They would be, in my opinion, present in all directions, and cellular structures and the size of cellular structures, the lambda, is actually used in RDE work as a design criterion. However, the pressure in an RDE combustor, particularly with an outlet nozzle, a plug nozzle, is significantly high. And so the cellular structures in a typical RDE combustor, the cell width would be very small, typically below 1 millimeter. So they would be very, very difficult to observe. But I think they are generally present.
Okay. Now I think the webinar should be finished. Thank you again, Professor Deiterding. To our speakers, Dr. Ren and Professor Deiterding, thank you for sharing your pioneering research and engaging with our audience. On behalf of the Combustion Institute and the ASPSCC Organizing Committee, thank you all for joining us. This concludes today's webinar. Have a nice weekend. Okay, bye.
Bye-bye.
Bye-bye.
Bye-bye.